Good afternoon, everyone. My name is Arka Roy, and today I will be presenting my PMRF Annual Progress Review Seminar on the topic titled Automated AI-Driven Low-Cost Respiratory Health Analysis System Design Using Respiratory Sounds. So, this work is supervised by Dr. Udit Satija, Assistant Professor, IIT Patna. So this is the presentation layout. So I will be starting with introduction motivation, followed by a short introduction that what respiratory sound is. Followed by that, we'll be defining the problem statements, public available databases, literature review, and the work that I have done already. And at the end, conclusion and future work plans will be discussed. So the respiratory diseases such as chronic obstructive pulmonary disease or COPD, pneumonia, asthma, etc., they basically refer to some dysfunctionality in the lungs. Now, these dysfunctionalities can be occurred due to either bacterial infection, viral infection, air smoking, air pollution, etc. In recent years, we can see that the mortality rate due to respiratory disease has gone up significantly. And in addition to that, WHO has also confirmed that almost 3 million people die worldwide due to respiratory diseases. So what are the existing diagnostic modalities to assess the respiratory diseases? So they are such as spirometric measurements, peak flow meter based measurements, pheno test, sputum test, etc. However, most of these processes are highly laborious. They are not very much cost effective, and at the same time we cannot recommend all these tests to a wider range of age group of people. So we need some alternative diagnostic modality by which we can assess these abnormalities in the respiratory system. So for that, in our research, we'll be focusing on lung sound or the chest auscultation sounds, which we actually hear at the time of chest auscultation using stethoscope, as these sounds are highly linked to the abnormalities present in the lungs due to any of the respiratory diseases. So here is the human respiratory system that basically starts with the trachea or windpipe, then followed by that it divides into bronchus, and bronchus even subdivides into bronchioles. Now this ends at the alveolar sac or these little air blocks where basically oxygen diffusion process occurs. Now, while air traveling through this path due to turbulent airflow, the lung sounds or respiratory sounds are being produced, and which we can hear using digital any stethoscopes at the time of auscultation. Now, if the lungs is healthy, then the airflow process will be very smooth. However, in case of disease cases, due to clogging of mucus, sputum, etc., the path may get narrowed. And due to that, several adventitious sounds can be produced. For example, wheeze, crackle, pleural rub. For example, wheeze, it's a high frequency event, and this can be heard at the time of expiration. That means when we breathe out. And it basically corresponds to COPD and asthmatic diseases. However, in case of crackle, it is basically an inspiratory sounds, and it is quite lowered in the range of frequency or the spectrum. And it is basically corresponds to pneumonia, pulmonary edema, etc. So this is the overview of the problem statement that I will be focusing on in my PhD work. So this is the graphical abstract. So first work will be, the first agenda will be to create a low cost digital stethoscope, and which we'll be using to acquire the lung sound signals. Now, upon acquiring the lung sound signals, we'll be developing some methods based on signal processing and deep learning techniques to either classify the sounds into particular disease classes such as asthma, COPD, bronchus, bronchioles, etc., or we'll be classifying the events of the signals. For example, whether the signal is normal or having wheeze events, crackle events, etc. Now, upon developing these algorithms, we'll deploy these algorithms into the embedded processor or Android system, and the Android system or embedded processor will be connected with the stethoscope in a wireless fashion, through which we can transfer the data, and over here all the computations will happen, and you can see the classification results. And after that, we can even send it to hospitals, doctors, and even we can store it to create a database of our own, which can be used for future research. So these are public available databases. So till date, there are only three databases: ICBHI, chest wall lung sound, and respiratory database TR. And these two databases basically focus on huge variety of respiratory diseases. So we can employ this for respiratory disease classification. And the final database, it is basically specialized in diagnosing different severity levels of COPD. For example, COPD 0 basically refers to the very less severe COPD, and COPD 4 is the very severe case of COPD. So this is the literature review. In the literature review, we can see that people have tried to develop several classification schemes, such as 2-class, 3-class, 4-class classification schemes, where they consider healthy, pneumonia, COPD, asthma, etc. And they basically follow a predefined path. For example, pre-processing, then feature extraction, and use of traditional machine learning classifiers or deep learning classifiers. So over here, we can see that either they have used SVM, KNN, decision tree based classifiers, or in the recent years, we can see that only Shivu et al. He had used a CNN based method, which is a deep learning framework, to classify 6 different disease classes using ICBHI or the D1 dataset, and achieved a commendable accuracy of 98.7%. So let us start with the work that we have done. So this is the first work, which is basically called RDLI-net, RDLI-net. It stands for Respiratory Disease Detection using Lightweight Inception Network. So the works actually starts with pre-processing the lung sound signal. First, we resample the signal at 4 kilohertz. Followed by that, we have segmented all the signals into 5-second frames with a 50% overlap with the next adjacent window. Followed by that, we have removed the baseline wander noise using a DFT-based filtering method. Followed by that, we have done the amplitude normalization to normalize the signal's amplitude in between -1 to +1 range. After that, we have extracted the time frequency representation, such as log scale Bell spectrogram, and feed it to our proposed RDLI-net block to get it classified into 7 different classification targets. So over here, this is the architecture of the proposed block, which comprises several convolution blocks, depthwise separable convolution. So depthwise separable convolution is used to employ the power of reducing the number of computations and the number of training parameters. After that, we have used MFLI block, 2 stack of MFLI blocks. So the architecture of MFLI block is presented over here. And after that, we have actually used a gap layer or global average pool to get a 1D vector, and which is subsequently processed using a GLU classifier to get it classified into 7 different classes. Now over here, this is the MFLI block. So MFLI basically stands for multi-scale filtering lightweight inception block. So we have modified the existing inception block by introducing the modification in the path 2 and path 3, which basically employs depthwise separable convolution, which further reduces the number of computation in the inception block itself. So that is the modification that we have done. And on top of that, one of the major novel thing is that the model is very lightweight, and we have incorporated all 3 databases. Over here, we can see that every work basically focuses on a single data set to accomplish their work. However, we have considered all 3 public databases to employ this classification task. So to show that the RDLI-net is really a lightweight network, we have shown the parameter study, and we can see that only 12,000 parameters, 12,942 parameters it requires to construct the whole model, even though the model comprises 42 layers. And this is the TSNE plot of the raw lung sound. And these we have done 3 tasks. One is the 7-class classification using all 3 databases, and to show that our model basically performs well than the previous published work, we have also considered the schemes like 6-class classification using only D1, asthma classification using only using D1 and D2. So over here in task 1 and 2 and 3, we can see that after using the RDLI-net, all the classified signals have basically created a very compact form of embeddings in the embedding space using a TSNE plot. So over here also we can see that embeddings are quite compact in nature. So here we have done the quantitative analysis using accuracy, recall, precision, F1 score, which are pretty much standard measures to quantify any classification task. So over here we can see that in all the cases we are getting a very decent amount of accuracy, recall, and in terms of other metrics too. And here is a comprehensive discussion that ReadLinet itself is again, it's a lightweight network. So we can see that a standard model, they basically comprise 138 million parameter, 4.2 million parameter. However, we just need 12,000 parameters to classify these respiratory disease classes. And in terms of accuracy also, we are beating each and every networks that has been proposed previously. So over here, we have shown the class activation maps to remove the black box nature of the model. So over here, we can see that this is the healthy class. So in case of healthy, the most of the energy is basically concentrated in the lower frequency region, and model also tries to look at those regions only. However, in case of URTA, we can see that there is high frequency events are there. So the model also refers to the high frequency event to get it classified into URTI class. So this is our second work, Asthma CLNet, which basically stands for asthma classification using supervised contrastive embedding learning network. So over here, we have done the pre-processing followed by mail spectrogram extraction. After that, we have segregated the whole data set into three different classes. One is the positive class, anchor class, and negative class. Now, positive and anchor, they are basically coming from the same class, and negative is coming from some other class other than from which the positive and anchored is coming. Now we have constructed a lightweight embedding extraction module, which basically extracts some compact embeddings from these given input mail spectrograms. Now the leap module has been trained in a parameter shared fashion such that it can produce the embeddings in such a manner that positive and anchor, in between these two, the distance will be minimized. However, in case of anchor and negative, the distance will be maximized. So therefore, we have trained this leap module using a contrastive loss function, that is a triplet loss, which basically employs the supervised contrastive embedding learning. Now, upon training this model, after extraction of good features, we have transferred this frozen weights and then converted all the mail spectrograms into some embedding, and then we have used a very shallow neural network model to get classified into either healthy or asthmatic class. So over here, this is the architecture of the lead module. So this is a kind of ReadLinet kind of architecture. However, over here we have introduced a residual skip connection in the inception block to reduce the overfitting. And over here also we have employed the depthwise separable convolution to further reduce the parameters. So this whole network basically comprises 18,000 parameters only. Okay, so to show that the leap module basically extracts very good amount, good kind of feature. So over here we have shown the raw lung sounds TSNE plot, and this is the TSNE plot of the embeddings that is extracted by the leap module. So we can see that there is a clear-cut difference between asthmatic class and healthy class. So any linear classifier, for example, the shallow classifier that we have used, it will classify very easily. So over here that we can see that within a very small number of epochs, we are getting very high accuracy. So over here to illustrate the same, we have used ROC AUC curve, the classification confusion matrix. So over here we can see that there is we are getting very less misclassification errors over here. And to quantify these whole things into some numbers, we have again done analysis using accuracy, sensitivity, etc. So we can see that our model is achieving 98.54% accuracy, and we are beating each and every methods that is being proposed in the literature. And around 28%, 24% margin we are setting over here for asthma classification. So this is the ongoing work. So we are, as I had previously told, that we'll be developing a low-cost digital stethoscope. So we are trying to do that using a very low-cost low-cost stethoscope market available. So we just cut it at the point of earpiece and then inserted a microphone over here. This is the acquisition circuit. After that, while acquiring the signal, we converting the analog signal into digital using A to D converter, and then feed it to the Raspberry Pi microcontroller. And over here we have dumped the SMIL code, and the model basically is processed over here, and the classification results will be shown in the LCD screen. However, this is at very early stage, so this needs several modifications as well, and till now we have not fabricated the PCB and all, so this is a very first kind of lab prototype. So here we'll be discussing about the conclusion and future work. So as we can see that we have established that lung sound plays a pretty important role to identify the respiratory diseases, and we have already shown that as these models are being very lightweight in nature, we can actually transfer this model to a real-time clinical scenario and create a point of care device which will be used for respiratory disease screening. And in terms of future work, so as we have showed that the COPD3 database, it comprises of different COPD severity levels. So we'll try to develop some methods to quantify or to classify the COPD severity conditions using respiratory sounds. Then we also try to classify the respiratory sound events, that is whether the sound is wheeze, crackle, etc. And finally, upon developing all these methods, we'll create a standalone system to analyze the respiratory health using lung sound. So that will be our future work. So these are the publications. So this is the IEEE transact. This has been published in IEEE Transactions in Instrumentation and Measurement. Followed by that, we have published a paper that asthma CLNet paper in Interspeech Conference, and we have also done a nonlinear neural network based asthma classification, and we had published this in IEEE MIMIA conference. And another paper is on actually STAC, which basically uses multi-scale representation of neural network. And this is basically in under review. So these are the references that we have used to create the presentation. Thank you.